In this video, we shall solve some problems when integrand is a function of more than two dependent variables. Let us take the first problem. Prove that the shortest distance between two points in a Euclidean three-dimensional space is a straight line. In this problem, we have to prove that the shortest distance between two points in a Euclidean space is a straight line. Proof: in the three-dimensional Euclidean space, define a curve by the equations y equal to y of x, z equal to z of x. Let pxyz, p of x, y, z, and q of x plus dx, y plus dy, z plus dz be two neighboring points on the curve joining the points A x1 y1 z1 and B x2 y2 z2. The total distance between the points A and B along the curve is given by I equal to integral from x1 to x2 of 1 plus y dot square plus z dot square dx. Here y dot equal to dy by dx, z dot equal to dz by dx. Suppose this is equation 1. The functional I is shortest if the integrand must satisfy the Euler-Lagrange equation, that is dou f by dou y minus d by dx of dou f by dou y dash equal to 0. This gives d by dx of y dot by f equal to 0. This implies y dot by f equal to some constant a. A is a constant. Therefore, y dot equal to af. This implies y dot square into 1 minus a square minus a square into z dot square equal to a square. This equation second. And z dot square into 1 minus b square minus b square y dot square equal to b square. These are the two equations. Solving these two equations for y dot and z dot, solving the equations 2 and 3 simultaneously, for y dot and z dot, we get y dot equal to plus minus a divided by root of 1 minus a square minus b square, and z dot equal to b divided by root of 1 minus a square minus b square. That is nothing but y dot equal to plus minus c1 for c1 equal to a into root of 1 minus a square minus b square, and z dot equal to c2 again plus minus for c2 equal to b into root of 1 minus a square minus b square. Here c1 equal to a divided by root of a square 1 minus a square minus b square, and here c2 equal to b divided by root of 1 minus a square minus b square. If we integrate equation 4 and 5, integrating equation 4 and 5, we get integration of y dot x dx equal to y, which is equal to plus minus c1x plus some function of z, because here z is treated as constant, and integration of z dot dx equal to, this implies this equal to z, this is equal to plus minus c2x plus psi of y, here y is treated as constant, where these are the equation 6, where phi z and psi of z, psi of y are constant of integration and may be the functions of z and y respectively. Thus, the required curve is given by equation y equal to plus minus c1x plus phi z and z equal to plus minus c2x plus psi of y. But these equations represent a pair of planes. The common point of intersection of these planes is the straight line. Hence, the shortest distance between any two points in Euclidean three-dimensional space is a straight line. This proves the statement. Now, example second, show that the geodesic defined in the three-dimensional Euclidean space by the equations x equal to x of t, y equal to y of t and z equal to z of t is a straight line. In this problem, we have to show that the geodesic defined in the three-dimensional Euclidean space by the equations x equal to x of t, y equal to y of t and z equal to z of t is a straight line. We shall write the solution of this problem. Solution. The representation of a curve in the parametric form is not unique. A curve in three-dimensional Euclidean space can also be represented by the equations x equal to x of t, y equal to y of t and z equal to z of t, where t is a parameter of the curve the distance between two neighboring points, the distance between two neighboring points on the curve is given by ds square equal to x dot square plus y dot square plus z dot square dt square. Hence, the total length of the curve between the points P at T0 and P at T1 is given by integral I equal to integration from T0 to T1 of x dot square plus y dot square plus z dot square raised to half dt. Suppose this is equation 1. This curve, the curve is a geodesic. If the length of the curve I is extremum, this happens, or this is a true if the integrand must satisfy the Euler-Lagrange equations. Dou f by dou xi minus d by dt of dou f by dou xi dot equal to 0 for all I equal to 1, 2, 3 and so on, with xi equal to xyz. Here, when dou f by dou xi equal to 0, and dou f by dou xi dot here, dou f by dou xi equal to 0 and dou f by dou xi dot equal to xi dot divided by f for all I equal to 1, 2, 3. This implies that x dot equal to af, similarly y dot equal to bf, z dot equal to cf. Simplifying these equations can obtain a square minus 1 into x dot square plus a square y dot square plus a square z dot square equal to 0, b square x dot square plus b square minus 1 y dot square plus b square z dot square equal to 0, c square x dot square plus c square y dot square plus c square minus 1 z dot square equal to 0. This is the set of three equations we can obtain from above equation dou fi by dou xi dot equal to xi by fi and dou f by dou xi equal to 0 in Euler-Lagrange differential equation. Now, this system of equation is consistent if determinant of the coefficients equal to 0, that is determinant of a square minus 1, a square, second row b square minus 1, b square, third row c square minus 1, this determinant equal to 0. If we solve this determinant, we will get a square plus b square plus c square equal to 1. Therefore, x dot equal to a divided by root of 1 minus a square minus b square into z dot. Y dot equal to b divided by root of 1 minus a square minus b square into z dot. Z dot is not equal to 0. Similarly, y dot is, therefore y dot will not become 0. This is equation 4. Integrating equation 4, we will get x equal to c1z plus phi of y, where c1 equal to a divided by root of 1 minus a square minus b square, and y equal to c2z plus psi of x, where c2 equal to b divided by root of 1 minus a square minus b square. Here, phi x and psi x are constant of integration, and may be the function of x and y respectively. Equations 5 and 6 represents the planes. The locus of the common point of these planes is the straight line. Hence, we can conclude that the geodesic in three-dimensional Euclidean space is a straight line. Thank you.